Okay. Hello, everyone. My name is Ajay Jacob, and I am the Director of Projects at the California Dreams Hub. Today, we have Professor Sriram Krishnamoorthy from UC Santa Barbara giving us a talk on beta gallium oxide epitaxial growth and vertical power devices. Professor Krishnamoorthy received the bachelor's degree in electrical engineering and physics from the Birla Institute of Technology and Science from Pilani, India, and a PhD degree from Ohio State University. Professor Krishnamoorthy is currently an associate professor in the materials department at the University of California, Santa Barbara, where his group works at the intersection of materials, electrical engineering, and physics to study and engineer next generation ultra-wideband semiconductors such as gallium oxide. His research interests are in the area of epitaxial growth, electronic transport, design, modeling, micro and nano fabrication, and characterization of optoelectronic devices for a wide range of applications such as power electronics, high-frequency electronics, and ultraviolet electronics, optoelectronics. He has authored or co-authored publications on several topics covering gallium nitride interband tunnel junctions for efficient Hall injection in 3-nitride optoelectronic devices, MBE growth of 3 nitrides, gallium aluminum oxide thin films and heterostructures, MOVP of ultra-wide bandgap gallium aluminum oxide thin films and heterostructures, and high-performance lateral and vertical power device and transistors based on gallium oxide. So it's my pleasure to invite Professor Krishnamurthy to the stage. Go ahead, Sriram.
Thank you, Ajay. I'm very excited to share about our recent research efforts in beta gallium oxide epitaxial growth and vertical power devices. A huge shout out to my team here in UCSP. We work closely with Professor Jim Speck in the materials department as well. And I would like to thank our collaborators, Kaima Technologies, National Labs, AFRL, US Naval Research Lab, and our circuit collaborators at Ohio State. I would like to also thank the funding from ARPA-E program, the Coherent 26 Foundation, and also we have ME Commons project through the CLOS Hub in North Carolina. So I'd like to thank all of the funding agencies for supporting this work. So I think the idea behind using wide bandgap materials for power electronics is the fact that when we increase the bandgap of a semiconductor, it can generally hold much higher electric field across it. So going from the traditional power semiconductor, which is silicon, to say silicon carbide and gallium nitride, you go from a couple hundred kilovolts per centimeter to about 3 megavolt per centimeter. And so as the bandgap increases, the breakdown field goes roughly as the square of the bandgap. And so the electric field handling capability of a wider bandgap semiconductor is significantly higher than silicon. So stretching that idea a bit further, if we go to newer materials like gallium oxide, then we can further have a much higher electric field across the device. And the on resistance of a power switch that's made using such a wide bandgap material goes inversely as a cube of the breakdown field. And the breakdown field goes square of the bandgap. So now we can see there's a huge advantage in going to wider and wider bandgap materials from an on resistance perspective. And the most simple way to think about that is for a given blocking voltage, we need to support the blocking voltage across a much thinner layer as we go to wider bandgap materials. And that's captured through the figure of merit, the Baligas figure of merit that's shown over here. So, so when we go from a material like silicon, we can get a very enhanced trade-off in terms of the on resistance and the breakdown voltage. When we go from silicon to wide bandgap materials. And our idea here is that if you go to even wider bandgap, the so-called ultra-wide bandgap materials, this impact can be further amplified. So that's at a device level. But if we make a device, a unipolar device, which switches at a higher frequency, then the inductors and capacitors that are part of a typical power circuit can also go down in size. And if the on resistance itself is lower, then the demand in terms of heat sinking goes down. So overall, at a system level as well, there's going to be huge size and weight benefit and performance benefit or swap benefit. So that's a case for going to wider and wider bandgap materials. And why gallium oxide specifically, right? So before that, I would like to also maybe give a use case or pitch for why we generally need higher voltage switches. So right now, the highest voltage switch that you can get, power switch you can get, is a silicon IGBT, 6.5 kV, and silicon carbide power MOSFETs, which are at either 1.2 kV or 3.3 kV range. So if you have a high voltage system, then you need to stack multiple of these modules in series and then control them synchronously to be able to realize a high voltage system. Whereas if you can go to an individual device or module that's rated at a much higher voltage, so that can dramatically simplify the overall system complexity and the control part of it as well. And so that's another argument to look for new materials that can support the single device, or a module can support tens of kilovolts instead of stacking multiple modules in series. So this kind of application interest is particularly relevant now in the context of AI data centers. So right now, the distribution in a data center is at 415 volts. So 415 volts AC distribution that comes into the rack, compute rack, and then you convert that to lower voltages, and then that goes to even lower voltages for the GPUs and TPUs, right? So this is a paper from NVIDIA where they envision a future where by going to a much higher voltage DC distribution, so going directly from 13.8 or say 35 kilovolt AC to a 800 volt DC distribution within the data center, and then taking the 800 volt distribution directly to the compute rack, and then locally doing the power conversion down to the GPUs. So by going from this 415 volt AC to 800 volt DC, one can dramatically reduce the conduction losses. So basically, you reduce the current draw, and so that reduces the I square R loss. And in this estimate that they worked out, so that gives about like a 5% improvement in the end-to-end power efficiency, which is a big deal because 5% of a huge number is still a very huge number, right? And to enable a technology like this, I think one needs high voltage transistors and diodes, because that's going to go into these solid state transformers. And so there is a case to develop these high voltage switches for any kind of high voltage system, and solid state transformers may be one example of that. And if you look at a solid state transformer, which I grabbed this picture from the Freedom Center website at North Carolina State University. So here you can see that it's essentially the heart of this is the semiconductor switches, right? The transistors and the diodes. And so these power transistor diodes and transistors and diodes basically are heart of any power converter system or a solid state transformer. And the simplest way to think about these power switches is just making it analogous to a mechanical switch. So when the switch is closed, you want close to zero resistance for the switch, right? So the on resistance, this will be the operating point of in a power transistor in the linear regime. So you want this voltage drop to be as close to zero as possible. So you need the resistance of the switch to be as low as possible. And the off state would be over here. And so essentially, we would like to get a high blocking voltage. And so a combination of high blocking voltage and low on resistance makes the switch exciting. And this trade-off between this on resistance and the blocking voltage can be made much better when we go to wider and wider bandgap materials, right? So hopefully I've given a background of why we need these switches. And this is where gallium oxide gets exciting, because gallium oxide has a bandgap that's 4.6 electron volts, much larger than silicon. a bit larger than gallium nitride and silicon carbide. And one exciting aspect of this material is that we actually have bulk substrate technology available. So these are 6-inch edge-fed grown, melt-grown substrates from Japan. And you can buy 4-inch substrates off the shelf even today, and 6-inch would be like a special order. But essentially, this technique, the edge-fed growth technique, is the same technique that's used for pulling out sapphire from a melt. And we all know how sapphire scales well to larger areas, and it's low cost. And so eventually, with enough volume, this could be a great thing to have, a bulk substrate technology that can be scaled to larger areas, because power devices, especially the power devices that are required for high voltage applications, generally also need high currents. And so the devices themselves are going to be like huge, and having a bulk substrate platform is going to be very important. So it's the only ultra-wide bandgap semiconductor that can be pulled out of a melt and still doped N-type. So you can get N-type doping, control over a large range, and large area substrates are available. And if we make just a back of the envelope calculation of the on resistance breakdown voltage trade-off for gallium oxide, we see that when you cross 10 kilovolt, this can be, in theory, 10 times lower on resistance than silicon carbide. So that makes it very exciting. So at the lower voltages, gallium nitride and silicon carbide are already doing great. There's an ecosystem out there, and lots of exciting products are coming out. And so we think for a new material like gallium oxide, the use case could be at a much higher voltage that is harder to access with the current materials. And the other important aspect in a power switch is also the fact that you need to have shallow dopants. So shallow doping is very important. So when I mean shallow doping, what I refer to is that the energy level of the dopant below the conduction band is comparable to thermal energy. And that is the case for gallium oxide. So for gallium oxide, we can actually get dopants which are just a kT below the conduction band. And so you actually get close to 100% ionization efficiency at room temperature for these dopants. And that's kind of important because in other materials like diamond, which would be the ultimate material in terms of band gap, or aluminum nitride, it's harder to get shallow dopants, right? And why is that important? Because you need shallow dopants, you need full ionization at room temperature for the on state to get enough carriers to reduce the resistance of the switch. But if you don't have a shallow dopant, then you end up putting a lot more dopants to get fewer electrons. That's okay. But under reverse bias, these dopants can field ionize and create a much higher electric field. And so the trade-off between the on resistance and breakdown voltage is actually worse for a material that has deeper dopants. Okay, this was actually worked out as a modification to the standard Balliger figure of merit in this paper from Jim Speck's group in 2020. And so putting this together, it turns out that gallium oxide is quite a compelling case for looking at gallium oxide as the switch when you cross to much higher voltages, and especially having bulk substrates is appealing, and the shallow dopants are also appealing. And so these are basic ingredients that make the material exciting. But more than that, high electric fields have already been reported in this material. So 4 to 5 megavolt per centimeter has been measured by multiple groups, across the US, Japan, and Europe, and China. And so this value, this experimentally measured value of electric fields in the device, is actually higher than the theoretical field of gallium nitride and silicon carbide. So the high field promise is quite there, and it's been seen by multiple groups. So I think these ingredients make it kind of exciting to work on this new material system, to develop the material science, growth, and try to make a nice high voltage vertical power switch. So that's been the focus of my group. So in my group, we do both growth and devices. In terms of growth, we use this Agnetron Agilis reactor research reactor 2-inch capability. We use the standard precursors that are used in other compound semiconductors like triethyl gallium, trimethyl aluminum. And we use ultra high purity oxygen as the oxidizing precursor. And silicon is a dopant for gallium oxide. So silicon substituting the gallium side as a shallow dopant. We use dilute silane for doping and argon as a carrier gas. So right now the reactor is configured with about 18 centimeter distance between the shower head and the chuck, but we have the capability of bringing this closer, what is referred to as the closed injection shower head geometry. So that's possible. That's part of our future plans as well. So the first thing that's interesting that we observed in the growth, MOCVD growth of gallium oxide is that the growth window is actually fairly large. So gallium nitride needs at least about 1000 C and higher to crack the ammonia precursor and to have sufficient air atom mobility on the surface. Whereas here, gallium oxide, high quality gallium oxide can be grown even at temperatures as low as 600 C. And so this is experimentally measured Hall data as a function of electron concentration from Hall measurements. So we can maintain smooth surface morphology, a very sharp doping profile when we try to grow colder. This can be used to our advantage in terms of growing these materials on substrates. So typically we grow on insulating substrates. So insulating substrate it's doped with iron as the compensating dopant. And this iron that we have in the substrate can actually get into the epitaxial layer. So being able to grow a low temperature initial layer or nucleation layer on gallium oxide can help us really drop off the iron surface riding into the film to within a tens of nanometers close to the substrate. And then once we do the low temperature layer, then we can ramp up the reactor temperature and grow high quality doped layers. Okay, so having this large growth window for this material system is quite exciting, and so that helps us get sharp doping profiles. It helps us do this kind of engineering the stack to be able to get high mobilities. So putting these ideas together, by figuring out the surface preparation techniques, low temperature initial layer and high temperature channel layer, we've been able to get across the board enhancement in electron mobility in these films. And you can see the wide range of doping capability we have, 10 to the 16 to 10 to the 20, which nicely scales with the flow of silane. And so this helped us achieve some record results in terms of electron mobility in the channel layer. And these channels are also high electric field handling, capable of handling high electric fields. So for instance, with just 2.7 microns of gate drain distance, we're able to block 1 kilovolt. So that translates to an average electric field of about 4.2 megavolt per centimeter, which is higher than the theoretical electric field handling capability of gallium nitride and silicon carbide. So basically, the large growth window and helps us get high mobility, and we can then translate that to high handling electric field handling capability in these devices. So, but these lateral topologies are okay for lower voltages. Eventually, we need to get to low doped thick epitaxial layers. So we need large thickness to be able to hold block higher voltages, and that would then necessitate high purity material, because we need now the doping to be less than 10 to the 16, because if you have a triangular electric field profile, then you need sufficient low doping and high thickness of the drift layer to be able to maximize the area under this electric field curve, right? Which is basically the blocking voltage. So there is a need to develop techniques that can realize large thicknesses of these layers with low doping concentration, negligible compensation, and high carrier mobility in these structures. So we started out some of this effort with MOCVD. So this is some recent work where we've been able to grow 4 to 6 micron thick films. We've been able to reduce the unintentional background doping in the material to low 15s, 10 to the 15s. And then by systematically varying the silane flow, we can control the doping in the film below a value that's 1e16. So these are super pure, more than parts per billion pure films. So we've been able to demonstrate that using MOCVD here in UCSB. And you can see this nice variation of the doping profile as we go to higher and higher silane flows. And we've also verified that the cost for electrons in this film is actually silicon that we have in the film. So we've been able to make a one-to-one correlation between the measured electrons to the silicon measured from the SIMS measurement or secondary ion mass spectroscopy measurements. And we've been able to get record electron mobilities close to 200 centimeters square per volt second for the low doping range, all the way from 315 to 1e16 range. The reason this is flat is because in gallium oxide, it's a low symmetry crystal. There are lots of phonon modes. There's a strong electron-phonon coupling and flow-leak interaction. So the theoretically expected mobility at the low doping regime is indeed close to 200. So we've been able to get films that are close to theoretically predicted values in terms of electron mobility. So we do have these high quality films in gallium oxide, and if you put that together in the literature, so generally in the literature, when we get to lower electron density values below 10 to the 16, you start to see a drop off in the mobility because of compensation effects. But by carefully tuning the growth conditions, we've been able to cross that barrier and get a much higher electron mobility in these films with intentional doping. So we've been pushing this further, trying to access even lower doping, much larger thickness. So Carl Peterson in my group is going to be presenting a number of papers in IWGO. This is basically a conference, a workshop that's scheduled in a few months in Maryland, in the University of Maryland. And so this is a week-long workshop where we have attendance from all the best groups working on this area. So Carl is going to be presenting some more recent updates to this. So achieving high electric fields at the junctions, up to 4 megavolt per centimeter, translating to high figure of merit, and also a growth along a new orientation of crystal with high purity, resulting in devices that can block up to 7 kilovolt using MOCVD. And to be able to achieve these results, we had to go back and look at the crystal structure more closely and analyze the effect of the orientation on process damage. And we also learned that certain orientations are actually more susceptible to ion damage. And so we had to come up with processes that are less damaging and so on and so forth. So this is going to be presented later in a few months by Carl. And Carl is actually in the job market, so he can do growth and devices, so it would be a great hire for anyone in this ecosystem. Okay, and again, why am I emphasizing this low doping regime? Because that's what you need to get to high voltage devices. So to get to something like 6.5 kV, we need thicknesses in the range of tens of microns of material with low doping. And so getting this combination is tricky. And in the ME Commons program that we have with the CLOS hub, Kaima Technologies was the lead for that project. They've been able to get some outstanding results, domestic EPI results. So these are been published very recently in the special issue on gallium oxide just this month. And essentially, they've been able to, so this is a paper from Carolyn Riley and Jacob Leach at Kaima. So they have been able to demonstrate up to 50 micron thick epitaxial layers using halide vapor phase epitaxial growth. So this is work done by Kaima, and we had access to some of this EPI through our project, and we've been able to do high voltage CV measurements to confirm that actually down to more than 10 to 12 microns into the layer, the doping is flat, and it's actually in the mid-15s regime. And that's exactly what you need. You need mid-15s doping and tens of microns of thickness to be able to hit 6.5 kV, 10 kV, and these higher voltage devices. So lots of exciting progress in the last few years in terms of the epitaxial growth capability, both in Japan and in the US. Okay, so that is the section in my presentation on growth. Now, if we switch gears and talk about some device research in my group, we do both growth and devices. So we have been trying to make these high voltage devices using a variety of topologies, using high K dielectric field plates, using charge balancing techniques, using dielectrics, and also geometry based topology. So essentially trying to make a trench out of the device and reduce electric field in the device through careful electric field engineering, and also combining gallium oxide with other p-type oxides like nickel oxide and chromium oxide to kind of overcome the issue with gallium oxide that there's no p-type doping available, right? And even if you found a p-type dopant, the valence band is very flat, so the holes wouldn't move much. And even if we manage to get holes in the valence band, there is a strong polaron formation in this material. So you would self-trap the hole and lose the hole. So essentially, there are multiple levels of challenges in getting p-type gallium oxide going. And so there's a motivation to now integrate other oxides, p-type oxides with gallium oxide. So I'll give you a brief highlight of some of these efforts, and then towards the end of the talk, I will highlight some recent results on transistors using this material. Okay, so the simplest topology would be to just put a field plate in. So if you have a metal semiconductor junction, we're going to have electric field crowding at the edges of this metal over here. And the simplest way to deal with this issue is to add a dielectric and a field plate metal, and we can spread out the electric field, and you still have two edges where the electric field is the maximum, right? You can spread out this field into these two peaks over here. So now this works quite well in most semiconductors. So to further push this, we've been exploring using high permittivity dielectrics. So basically, we can add dielectrics which have a much higher dielectric constant. And what this lets us do is it further helps us in spreading out the depletion region, and the electric field can be lowered by using a high permittivity dielectric instead of a low permittivity dielectric for the field plate oxide. So we experimented with this idea way back in 2021 with an epi from Kaima, from Jacob Leach. These are thin, like 1.7 micron, relatively heavily doped epitaxial layers. And we added these high dielectric constant field plates. In this particular case, it was a superlattice of barium titanate and strontium titanate that got annealed and mixed up, and with an effective dielectric constant close to 300. And by doing this, we were able to get 600, close to 700 volt breakdown in this thin epitaxial layer without compromising the on state of the device, right? So the no field plate device and the field plate device had the exact same on state characteristics in terms of on resistance, the turn on voltage, and so on. But we got a huge improvement in the reverse blocking capability, which is exactly what we want. And so we were able to get on resistance which are below 1 milliohm centimeter square at 600 volts using this approach. Later, we extended this idea by using a low dope thicker epitaxial layers, 11 microns of epitaxial layer and with low doping. And you can look at these log IV curves. These are very ideal diodes, Schottky diodes, essentially ideality close to 1, nicely scaling with area. And the breakdown voltage was also constant across 50 micron diameters to 300 micron diameters in this particular device. And we were now able to get up to like 2.2 kV Schottky diodes on gallium oxide layers with a high K field plate. So these devices still have a triangular electric field profile because you have, when you deplete the charge, you have uniform charge and use Poisson's equation or Gauss's law. So basically, you will find the electric field is linear. You have a triangular field profile. But in silicon, you can actually do charge balancing. So essentially, you can have columns of p-type and n-type material, which if the charge is equal, then you can get a net zero charge in the depleted layer, which results in a flat or a constant electric field profile, and that gives you twice the breakdown voltage. So that's the concept of a silicon superjunction. So you get twice the breakdown voltage, but more importantly, the fact that you actually have these alternating pillars of P and N-type region means that you can actually now dope the material heavily and still deplete it. And so that actually gives you a much lower on resistance. So the win in a superjunction is not just twice the twice the voltage, but actually a much reduced on resistance, because now you're able to dope the material higher and still deplete it using these columns of charge balanced P-type and N-type materials. So to do something similar in gallium oxide is going to be hard because we don't have P-type material, right? So we were now thinking about ideas of using a dielectric and the fringing electric field within the dielectric to be able to now have a similar effect, superjunction-like effect in gallium oxide. And we tested out this idea in a lateral geometry first. We made some analytical models of this design, and you can effectively mimic superjunction by carefully choosing the aspect ratio of a structure, the width of these dielectrics, and the aspect ratio. If you carefully choose those values, then experimentally we've been able to show that you can actually get very high figure of merit, which at this point in 2022 crossed the silicon carbide line with just 5 microns of anode to cathode distance in a lateral topology. We were able to block close to 1500 volts on average electric field of 3 megavolt per centimeter. So one could kind of, so a new material with a new challenge in terms of not having P-type leads to, you have to come up with new ideas in terms of field management. And so using dielectrics carefully can kind of enable such novel devices. So the other way to engineer the electric field profile would be to go take advantage of the geometry, right? So in this case, a planar Schottky is going to have triangular field profile, but if we etch down this layer out of dielectric and have a sidewall metal, then we can have field cancellation, and we can reduce the electric field at this metal semiconductor junction. And we can push the peak electric field from the metal semiconductor junction into the semiconductor layer. And so if we get able to push the electric field into the semiconductor layer, then that basically means that the field emission tunneling under reverse bias is reduced. So this is the reduced surface field effect or resurf effect. And so in my group, we basically took this idea and then modified it to include high K dielectrics. And if we had high K dielectrics, we can actually further reduce the surface electric field compared to a low K dielectric. And what that helps us is that now you can start using a low work function metal, and you can make a Schottky diode with a low turn-on voltage while still preserving the reverse leakage because you're reducing the surface electric field. So it kind of removes the trade-off or modifies the trade-off between the on-state and off-state for a Schottky diode. So we further simulated these devices, and you can, if you engineer them carefully with the right aspect ratio, you can get to very low surface electric fields in these devices. Okay, and you can push the peak electric field within the semiconductor, and so this was kind of experimentally realized using platinum and ruthenium as the metal layer. And barium titanate as the high K oxide. And we were able to demonstrate tunability of the forward turn-on voltage. So lower work function metal like ruthenium gave us a lower turn-on voltage, still good current densities. And platinum gave us slightly higher turn-on voltage. And we also made large area diodes. These are 2 by 2 millimeter diodes that are relevant for power electronics. So essentially here we were able to measure on wafer currents up to 20 amperes in a 2 by 2 millimeter device using ruthenium as a contact. And what is outstanding is that the reverse leakage in these devices are close to noise floor and very low values. And when we scale the area of these devices, the breakdown voltage does suffer, which means we do have some weak spots. When we scale the area, we still need to understand the microstructure and the leakage mechanisms, and maybe killer defects in the epitaxial layers and so on. So these are open questions. These are important questions to look at when we try to scale the area of the devices. But nevertheless, we can see that the reverse leakage current in these structures are extremely, extremely low. And what is now more exciting is we did some capacitance measurements, estimated the stored charge in these diodes, and tried to compare it to silicon carbide bare die off-the-shelf components, and we are able to get lower charge, lower stored energy in these diodes compared to silicon carbide. So we actually have the lowest stored charge forward voltage product of any gallium oxide diode, with more than 1 kilovolt 1 amp rating in this trench high K resurf diode approach. So more recently, we have started working on adding these p-type oxides. So we've done nickel oxide. In this slide, I'm showing chromium oxide. So this is thin layers of P-like oxides, which give you a built-in potential close to 2 volts. So compared to a Schottky, you do suffer a slightly higher forward voltage drop, but the enhanced built-in potential here gives you outstanding reverse leakage characteristics, almost noise floor level leakage. And you've been able to make diodes with a few amps forward current and breakdown voltages as high as 3 kV. And so once we made these amp 3 kV, 1 amp, 3 kV diodes, we collaborated with the Ohio State University, Professor Jin Wang's group, to do double pulse measurements in these diodes. And then estimated or calculated the reverse recovery time in these diodes, which is presented in EPEC and the Applied Power Electronics Conference a few months ago. And so here we can get extremely impressive reverse recovery times in these diodes. So although we are adding a p-type oxide, that transport is dominated by electrons. So the reverse recovery is still very fast, unlike silicon PIN diode, where you worry about conductivity modulation, and reverse recovery is much larger time. So this reverse recovery time starts to look more like a Schottky diode, although we have a p-type oxide over here. So transport is dominated by electrons in our understanding, because these things need to be studied more carefully. So now these diodes, these are some of the highest test voltage and lowest reverse recovery charge reported for gallium oxide, and these numbers are promising. We did some benchmarking with silicon carbide, and the reverse recovery time is definitely smaller than silicon carbide at similar voltage rating. So that's quite exciting, and we continue to push some of these very recent results. And more recently in my group, we've been able to push these heterojunction diodes to about 10 kilovolt with reasonable on resistance, translating to a figure of merit that's very close to silicon carbide theoretical line. And this is a diode that survived 3 sweeps and even more, like 10 kilovolts. And this is basically the characteristics before and after the sweep. And if you translate, this is 20 micron thick epi, and if you translate this to an electric field at the junction, it works out to be something around 5 megavolt, 5.3 megavolt per centimeter. So this is very recent results to be presented in the Device Research Conference in Michigan later this month by EGen Liu. So we are starting to see these 10 kV diodes, and there is also reports from University of Florida. So they've been able to measure up to 13.5 kV in gallium oxide as well. So and there's lots of papers from China where they're starting to report high breakdown voltages as well. So it's quite an exciting time for the material. So that's the diode. So constant progress in terms of high voltage, low stored charge diodes. So in my group, in the remaining 5 or 10 minutes, I would like to highlight some work we are doing on the transistors or switches. So there is no p-type availability, right? And so we have to do a junctionless architecture. In this case, these are vertical FinFETs. So we define narrow channels, about 200 nanometer wide channels of low-doped gallium oxide. And then we use a metal oxide semiconductor junction on the sidewall of this fin for the gating purpose. And so then that way you gate from the sidewalls, both the sidewalls, and then you control the current flow from the source to the bottom drain, right? So it's a vertical FinFET, no junctions, no p-type layers involved, all unipolar. So hopefully these can be like fast switching transistors in the future. So this is the SEM image of the fib SEM image of the transistors we have made. You can see near vertical fins, nice corner rounding to manage electric fields in these devices. And we can see nice gates on the sidewall of these devices. The fabrication is a bit challenging, nevertheless, but we've been able to fine-tune this process over generations. And now we have a nice working process here in the UCSB Nano Fab, which is a fantastic nano fab for research. And so these are the vertical FinFETs. And earlier this year, Roy, so in my group, so we reported 1.8 kV transistors. So these are 1.8 kV transistors with 3.2 milliohm centimeter square on resistance. And the novelty here is that we added a field oxide in the bottom of the trench. When you add a field oxide, this can result in enhanced breakdown voltage as seen from this particular comparison. So without the field oxide, these devices broke down at 800 volts, but we were able to push it out to 1.8 kV by addition of the field oxide. So since we're working on bulk substrates, these devices actually have excellent on-off ratio. The off-state leakage current is pretty low. The on-off ratio is very good, 10 to the 9. And so that's because we have the benefit of working on a very high quality crystalline substrate that nicely follows onto the epitaxial layer in terms of the quality. And so even more recently, this is some very new data. It will be presented later this month. At the Device Research Conference. Again, Sriram went on to become a professor at NC State. So Sriram is going to present this in DRC end of this month. So we've been able to make 3.4 kilovolt transistors. Again, excellent on-off ratio, 10 to the 10. These are enhancement mode. Slightly higher on resistance in this case, and we know how to make this better in the future generations. And we're able to get breakdown very low reverse leakage for the transistor until it catastrophically breaks down at 3.4 kilovolt here. So the most exciting part about this particular device and this generation of device is actually when we compare this to gallium nitride and silicon carbide. So although gallium nitride and silicon carbide can theoretically hold high electric fields, but for devices, say a 3.3 kV device in silicon carbide, you actually need 33 microns of drift layer. And so this translates to an average electric field handling capability of about 1 megavolt per centimeter. And that's the same for gallium nitride as well. These are gallium nitride FinFETs from MIT. And so, whereas in gallium oxide, we are able to block 3.4 kV with just 11 microns of the drift layer, and which translates to about 3 times higher electric field handling capability in this material compared to GaN and silicon carbide. So I've plotted this average electric field as a function of the actual breakdown voltage. So normally, lots of groups report excellent high average fields at low gate drain distance in a lateral device or a low thickness epi in a vertical device. But scaling that to higher voltages is generally challenging. But here we've been able to simultaneously get high breakdown fields at high breakdown voltages. And these are some well-recorded results right now to be presented later this month in DRC. I would also like to give a shout out to an excellent result from Japan. This is 10 kilovolt transistor from Novel Crystal Technology. And so this is an amazing development for the field. So this is a very recent work from Japan. They've demonstrated 10 kilovolt vertical transistors in gallium oxide as well. Okay, with that, I would like to summarize that, using this low-doped epitaxial layers, we've been able to get the highest average field in any vertical power transistor, and more recently also some diodes, impressive diodes, and we're starting to switch these devices, and the diodes are showing some early promise in terms of the reverse recovery time, and so on and so forth. And again, a big shout out to my entire group here, and the funding agencies and collaborators. So with that, I would like to thank everyone for your attention, and I'll be very happy to answer questions.
Thank you, Sriram. Great presentation and a lot of results, incredibly lot of results, and even this year.